Swayam Prabha. Digital India. Educated India.
In the last couple of classes, we have discussed, I would say, the introduction to polymer physics course. We learnt about like how polymers are made very briefly, and then we discussed about the types and classification of polymers. And then finally, we came to a point on why study polymer physics. So, I already told you that in polymer chemistry, we learn about the synthesis of polymers, that is more chemistry aspect of it. And when we are doing polymer physics, we are looking at the universal features of polymers that are not much dependent on the chemistry. Okay, so I will illustrate that in the class today, and then like elaborate on like what exactly a polymer physics is composed of, and then briefly about the history of polymer physics. Okay, so let's get started. So what I told you in the last class is like polymer is a long chain of carbon. That's why we call it a macromolecule. And the main feature that makes it different is it is flexible. It is flexible because it can take many conformations and so on. And say now I want to go back and say how exactly this can be a property that is not property of the chemistry, but a property that is more like universal in nature. Okay, so let's imagine that we have two different kind of building blocks. One of them I am representing by say a circle, and another one is like say a triangle, and they are like forming like a polymer chain. So, for example, this is forming a polymer chain, something of that sort, and this is forming a chain something of that sort. Okay, and now if I look at how many conformations then each of these take, then the number of configurations that the left one has with circles will be more or less same as the right one will have with the triangles. And the reason why I am saying this is, let's say using the squares, if I am forming this kind of conformation with the triangles too, I can form the same kind of conformation, right. So, if I want to look at like how many conformations the polymer chain can have starting from like these two building blocks, it appears that the number of conformations will not depend on what the building block is, but it will depend on like how many of those blocks are present here. So, in both these cases we have 1, 2, 3, 4, 5, 6 blocks, and the same thing here we have 1, 2, 3, 4, 5, 6 blocks. So, the number of conformations will depend on the number of blocks that we have. So, as I increase the number of blocks in the circular case or a triangular case, we will increase the number of conformations, and in the language of physics, as the number of conformations increase, the entropy increases, or we can say entropy is a function of the number of conformations. We will detail about this in later. So, since the entropy of the chain will be simply a function then of the number of blocks, because we said that the number of conformations is a function of number of blocks and not exactly like what the block is composed of. We have identified at least one feature of the polymer chain that is not dependent on the details of the chemistry, but it is more dependent on like how many blocks are connected together. In other words, what is the molecular weight of the polymer chain. Okay. So, this is like one of the examples that if I start to have larger number of carbons, we start to have more number of conformations, and then the properties that depends on the number of conformation, not the types of building blocks such as entropy, will be the same in different kinds of polymer chains. Okay. So, this is like the basic premise of polymer physics, that we have behaviors which are universal in nature, and that is the reason why we say the subject to be like a polymer physics, not a polymer chemistry. There is a sense of like universality in how things appear. So, in this particular case, you can see like we had like two different kind of building blocks, and they give rise to same kinds of behavior. So, this has a more general language of saying about it, and that is to say that we can build models which are referred as toy models that can give you the same behavior as the polymer chain itself. Okay. So, I will elaborate on that in this lecture. But one of the properties we want to look at in polymer physics, for example, is let us say if we have like a polymer chain, we are interested in the end to end distance of the polymer chain, and typically, since we said that the polymer chain can take many conformations, we do not talk about the end to end distance of a particular conformation, but something like the average of the end to end distance over many conformations. It turns out the average does not have much meaning in many cases. What is more relevant to us is something like the mean squared average of the conformation. And what we will show is we can build like toy models, which are referred as random walk models. And the common feature in all these models is that as I increase the number of blocks or the number of segments or the number of small steps that I am trying to model, I will see the end to end distance squared will increase in proportion to the number of the same things. Okay. And it turns out that many of the polymer chains indeed show this behavior, where their end to end distance squared is found to be proportional to the molecular weight of the chain or the number of repeat units. And m is like some number of segments or units in our toy model. Okay. So, what exactly that means is that we do not have to go to the detailed chemistry. We need not start with say looking at each of the carbons and what is happening there, what is present inside. For example, if I really zoom into a particular part of the polymer chain, indeed it has some kind of an structure, but that is of not particular relevance to that, whether it is like this or like that. It does not really matter to us how the polymer chain is being formed, as long as it possesses certain sets of features. For example, this is the behavior that we see in many polymer chains is something like this, which we refer to as the ideal chain behavior, and that we can also get from toy models. Okay. So, this is like one reason for doing polymer physics. The other reason is the following. Let us say if I want to look at from a purely chemist viewpoint, and I want to look at this entire chain of carbons. You probably know from the chemistry background, folks will of course know about it, that if I want to look at the detailed chemistry of this particular polymer, I need to perform something like a quantum chemistry calculation for this. Okay. And what that amounts to is solving what is known as a Schrodinger equation. That is a very complicated equation, and it turns out the Schrodinger equation has a solution only for very small molecules like hydrogen. So, as soon as the molecules become complicated, we have to go to like a numerical solution. That is also possible only for, I would say, small molecules containing say 10 or 20 atoms. So, if we talk about anything of the order of 10,000s of atom or thousands of atom, which is the case for polymers, it is almost impossible to do any kind of detailed quantum chemistry modeling. Okay. So, one reason for doing polymer physics is of course that the materials which are the polymers possess certain universal features, and the other reason is because we cannot do the detailed chemistry by following, for example, quantum mechanics. It is not possible today, and it is not likely to be possible in near future by the computational resources that we have in the world. Okay. So, this is, I would say, is the basic premise of polymer physics. One, quantum chemistry is not possible, and second, TWI models do work for many features. Okay. So, there are two essential approaches that are typically followed while doing this. One approach is that we start looking at the polymer chain, the detailed chemistry. We try to build a representation that we call a TWI model. Then we predict the behavior that we want to predict, and then finally we compare to experiments to see whether the same behavior is observed. Okay. That is one way of doing it. The other way of doing it is we look at an experimental result, we observe certain features, then we try to build a TWI model that give rise to same features, and then finally use the TWI model to look at other kinds of polymer chains of similar nature. Okay. So, I would refer to like one of them can be like a top down kind of an approach, and the other one can be a bottom up kind of approach. Okay. So, in one case I would start with the detailed chemistry of the polymer chain containing whatever groups that are present, and then using that we try to build some kind of a representation. For example, let us say this is my TWI model, where these segments now represent, for example, certain number of carbon atoms. We will talk more about this. These kind of models comes under a general class of random walk model, which by the way is a TWI model. Okay. And then we can predict certain features. I give an example of the end to end distance squared average. So, we predict features, and then we can do an experimental validation of that feature. And the other approach is we forget about the detailed chemistry, we get some experimental data, then we try to find certain patterns in the data or try to extract certain features from there. So, we observe features, and then we build a TWI model that also possess the same features. And now you see the two paradigms. In one case, we have started from the actual chemistry and try to somehow decrease the number of freedoms, try to make some kind of a representation that mimics the chemistry that we know, and then we try to predict the features, that is like starting from the molecular structure. In the other case, we start from say experimental data. In that case, it is more like a fitting kind of exercise where all we need is the models would give you the same value of the quantity or the same kind of an scaling of the quantity that we see in experiments. But then the advantage is that we hope for the most part that whether the toy model I get from the first approach or the second approach will also work for other types of system. So, we can use toy models to study similar systems, and it is then that these models become useful, because if we can get some physical understanding based on these models, then we can use that in our design strategy of polymers, in devising like polymers that will give you certain types of behavior and so on. Okay. So, this is why polymer physics become useful. It helps understand why the polymer chains are behaving in a certain way, although by a toy model, and in second way it can help us design new kinds of polymers once I understand what are the basic features of polymer chain that governs these kind of behavior. Okay. So, toy model is not entirely a new idea that is only present in polymer physics. The physics folks will realize that it has many commonalities with other toy models, such as Ising model for magnetism, that again is a toy model, but it gives you the magnetic phase transitions, and it is an excellent model. So, this is the kind of approach that we are following in polymer physics, and I would really say that the polymer physics is not really a very old field. It started like in 20th century, and we will mainly discuss the work of 2 or 3 main scientists in this area. One of them is Paul Flory, who was an American chemist, and he was in the year, so he was in the year 1910 to 1985. He did won a Nobel Prize in chemistry in the year 1974. He started as a chemist. He worked on polymerization reactions, but he also built very nice physical models which were like excellent yet very simple kind of I would say theory. So, he was a man with great intuition, and he has made excellent models of polymer physics, and we will discuss some of that in this course. Then there is a scientist named Sir Samuel Edwards from 1928 to 2015. He was based in Britain. He was a British physicist. Flory was an American chemist. And Edwards did some of the more rigorous kind of models that becomes like the modern treatments of polymer physics. And then there was another physicist, his name was Pierre Gildezenas. He was a contemporary of Sam Edwards, and he was a French physicist. He also won a Nobel Prize in physics in 1991. And so, these 3 people I would say have been the pioneers of polymer physics that we will discuss in this course. And in general, the Flory made some initial achievements. He I would say was pioneer of the basic idea why these toy models should be used in polymer physics. Then Sam Edwards made certain rigorous models that present the basis of today's polymer physics. And then finally, Dizennes added a new component to it, which is known as the scaling approach, something that is building on the Flory's idea, but that becomes useful in many applications of polymers, and it has much more sound physical basis. Okay, so I will probably stop here, and in the next class we start talking about the random walk models in polymer physics.